Hello warmly. Today we will calculate displacements using Maxwell's method for the beam that we see in front of us. But before we proceed with calculating the displacements and what it directly involves, we must first solve this beam for the state under external loading. That is, for all those forces and moments that are drawn here. To this end, we will start by releasing it from constraints, which means we will draw reactions at the points where supports are present. In our case, points A and C. Let's start with that. At point A, formally we should draw two reactions, the vertical reaction VA and the horizontal reaction HA. Here, in particular, if you don't draw it, nothing happens, because in this specific beam, we don't have horizontal loads. So HA, without any further ado, we can write as 0 and won't worry about it later. At VC, there is only the vertical reaction, so we have no dilemma. We calculate these reactions using standard static methods. Here, we might not always need to calculate all reactions in these tasks, but here we do so to ensure we're calculating correctly. We'll calculate them just to be sure. It is something we theoretically should know. In practice, it varies, so let's take our time with it. Reactions. We start by calculating moments at point C relative to point C. So we have them in order. I assume that a positive moment is clockwise, meaning moments that would turn this beam relative to point C. We consider clockwise as positive. V times the distance, 6m plus 20 kmm, which is this moment here. Subtract 20 times 2, subtract 10 equals 0. V equals 5, of course, kn. The sum of moments at point A. I could just as well calculate the sum y, but we want to check the solution at the end. 20 plus 20 times 4, subtract 10. Subtract. VC times 6 equals 0. And from this, we get that VC equals 20 plus 20 times 4. Subtract 10 divided by 6 equals 15 kN. At a glance, it seems correct, but let's formally write down the sum of vertical forces. So what's going up is positive. So we have VA plus VC subtract 20 equals 0. So we see that 5 plus 15 minus 20 is okay, equals about. So we calculated this correctly. And now, as we don't need to draw all internal forces, for example, we don't need vertical forces, we'll just draw the moment diagram. This can be done practically immediately at this moment, because what we really needed most was information about the moment occurring at point B. That's because for point A and point C, those moments are obvious. Normally it would be 0, but now, since we have transferred external moments here, so, respectively, at point A, we will have 20 tension at the bases, and at point C, 10 also tension at the bases. Parts will already be missing. At the moment we calculate moments at point B. Let's say we're calculating from the left side, it doesn't matter, but it will be more convenient. 20 plus VA times 4, moment at point B equals 20 plus 20 equals 40 kN times m. And indeed we get 40 here, so ultimately the diagram looks like this. These pluses are very fleeting. Generally, I am not a particular advocate of marking moment diagrams. I usually don't mark them, but now for simplicity we will mark them. And this is our bending moment. We write it with a capital M, and it has the dimension kn times m. We theoretically knew this, so having done it is nothing to be happy about. There's nothing to be happy about, let's move on. So now we have dealt with the external load topic. We proceed to displacement calculation. Let's start with vertical displacement of point B. To calculate the vertical displacement of point B, we first need to draw the entire beam diagram again. So let's discard these calculations for now, which won't make us happy anyway, and draw the beam here, which we will now calculate. It's basically the same beam, but differently loaded. At the moment, we don't look at what the initial or external loads were that are in the task description. Only at the given point B, which is point B at this moment, we apply a force with a value of 1. And now attention, it doesn't matter whether I apply it vertically up or vertically down. We agree that generally I will apply them vertically down because assuming for this beam, just intuitively it seems to me, that the load will cause the beam to deflect downward. So I hope that if I apply a unitary force in this way, the displacement will come out positive later. There's no need to worry too much about this. If it doesn't come out positive, we'll just know we assumed incorrectly. Similarly to before, we first calculate reactions. VA, VB, HA. HA equal to 0. We will note it immediately, we won't be dealing with it. And we will calculate the reaction for this beam. Although this is a straightforward beam, So, if someone has learned the mechanics of material strength well, it depends on which subject you calculated internal forces. They should be able to draw this diagram. Sorry, it should be VC, not VB. They should be able to draw this diagram by hand. But it varies, so we will calculate it step by step. What do we have here at point C? It's VA times 6 minus 1 times 2 equals 0 from this quickly. That VA equals 1/3. As a side note, we assume that this force is dimensionless. Therefore, Virginia is also dimensionless, and the moment diagrams will be almost dimensionless. There we'll have 1 or 1/3 times a meter. So this diagram will actually be in meters. We can draw it in advance. Here we will have a diagram like this. Let's call it small m. We can define it as, for example, small m at point B from the vertical force. So let's call it, for example, y, and it will be in meters. I don't actually need to calculate VC, and I won't. It's enough for me to calculate the moment at point B. Looking from the left side, we get that it is VA times 4. So it comes out very nicely that it is 4/3. And we quickly draw the diagram. Clearly, for the beam ends, for point A and for point C, that moment will be 0. Here, we will simply have moment 4/3, positive. That 4 is not very clear, but we'll know what it means. We've got such a diagram. And now let's move on to calculating the vertical displacement. We'll do the angle of rotation separately. We will completely skip the analytical integration. However, we will do graphical integration in at least, in quotes, 2 ways, because it's still the same theorem, and we will continue using the same rules. However, once we will use the definition directly, and once we will integrate using pre-derived formulas, which you can find in the tables, which I will link at the end. Now let's start by writing down the general formula. So, we have the following situation. I'm calculating YB. If I were to write this integrally, I would have that it's m times by m and dx, integrated over the length. However, as we will be graphically integrating it, let's write it down immediately in graphical form. 1 over EJ goes before the integral, and we integrate separately in the interval AB and BC. So, in the interval AB we have 20, 40. Length 4 meters. Integrated with a triangle 4/3. Of course, both figures are positive. We add the interval BC. In the interval BC, we have 40. Here, 10. Positive. The interval is 2 meters. And here we have again a positive triangle. 4/3. So now, if we wanted to integrate this by definition, then I need to break up the trapezoids first, or possibly calculate the location of their center of gravity. However, this will be rather unpleasant to execute. The formula for the center of gravity of a trapezoid we know at least theoretically. We could divide it into a rectangle and a triangle. We could divide it into 2 triangles. Each of these figures here, this one and this one. Let's try to divide it into triangles. So then we have the following situation. Maybe just enough to gain some space. We don't need this anymore, at least for now. We can return to this later if necessary. Let's move this whole analysis a bit to the side and return to reality. Now we need to separate it into triangles, as I mentioned. So we have 1 over EJ. And we divide it into triangles. And we divide the triangles in the following manner. Like this and like that. So this triangle is 20. And this triangle is 40. Fortunately, both are positive. Of course, both are still over 4 meters. And we integrate with a triangle 4/3. And with an identical triangle 4/3. So it is the same interval. We just split it into 2 figures, using the principle of superposition. Here, of course, there's a plus sign. Next, we break down the next triangle. And we get triangle 40, and triangle 10, plus, 2 meters, and 4/3. This is the same interval BC. So 3/4 is in this direction. And now finally we are moving to integration. We discussed graphical integration on another occasion. However, now we will directly apply it. So we have, in order, like this. Here we will be integrating in the same way approximately. So we take the area from the upper figure. From the lower, we take the height of the figure, where the upper one has the center of gravity. So we have 1/2 times 20 times 4. The center of gravity is here. So when we project it down, we will have 1/3 of 4/3. So 1/3 of 4/3. Add 1/2 times 40 times 4. We project it. Times 2/3 times 4/3. Add 1/2 times 40 times 2. Times. Project the center. It will be 2/3 times 4/3. Add 1/2 times 10 times 2. And the center is here. So times 1/3 times 4/3. Of course, we don't forget about 1 over EJ. I forget about it notoriously too, but we have to remember it. In this task, it doesn't have key significance, but there are tasks where it is very important, so we try to remember it. We calculate it quickly. We get 1160 over 91 over EJ. In a moment, we'll check if it comes out the same way by the second method. For now, I'll reveal the secret immediately, that it came out the same as it did for me when I calculated it previously. So it should be okay. So we remember this result. And now we move on to counting with the second method. In a moment, I will erase what is here. It is no longer needed. So this entire part related to calculating using this method is currently unnecessary for us. Now we will show ourselves as if the second method. I'm saying informally that this is the second method. It's still the same graphical integration. Now we are using a ready-made formula. It will appear here in a moment. Well, okay, we have the formula. It looks how it looks. In a moment, you will see that in application, it is much simpler than it seems. Of course, we write at first glance 1 over EJ, so as not to forget about it this time. And now we have this L6, which is length divided by 6, 4/6, times 2 times what's on the same side. So 2 times 20 times 0. We don't write that because there's no point in writing 2 times 20 times 0. Add 2 times what's on the same, 40 times 4/3. 2 times 40 times 4/3. Add, now crosswise, 20 times 4/3. Add, crosswise 40 times 0. We don't write that. Add 2/6. Second figure, 2 times what's on the same. 2 times 40 times 4/3. Add 2 times what's on the same. 10 times 0. We skip that. Crosswise 40 times 0. We skip. Add 10 times 4/3. And that's it. We get 4/6 times 2 times 40 times 3. Add 20 times 4/3. Add 2/6 times 2 times 40 times 4/3. Add 10 times 4/3. And it comes out the same, 1,169ths, which is 1,169ths EJ. As you can see, this method is much simpler. Usually in the next task, we will only use this method. However, it is also worthwhile to be aware that we can use this method of superposition, which we used in the previous task, to break down loads within a given section into their component parts. We will use this later when recalculating integrals, for which one of the figures will be a parabola, but you will see in the following tasks. Now, however, we will go on to the second part of the task. So, we have already calculated the vertical displacement of point B. Now we will calculate the angle of rotation at point B. So now how is it different? It is different in little. Of course, I return to this diagram with external moments. Because we will need it, it hasn't changed. Because the same external loads are still there. We still have the same beam. But we apply not a unit force, as we calculated in displacement, but a unit moment. So if we calculate the angle of rotation, we apply a unit moment. So here we have a 1. We calculate the reaction, and another Vc, so that each time, when the load changes, the reaction also changes. Horizontal is obviously 0. Here we have Vc, so we managed not to make a mistake, and so we calculate an analogy. At least one reaction here should be calculated. Let's say we calculate, from the moments at point 0, we quickly get V times 6, plus 1 equals 0. On the side note, here again it is indifferent. In which direction? Our unit force will be whether it will be right or left turning. It doesn't have any significance for us. And now again, to draw the diagram, we need to calculate MB. From the moments at point B, looking from this side, it is simply V times 4. This equals minus 4/6. On the side note, we have a rather interesting situation. We have a relatively interesting situation. Here indeed in general, in this task, since we do not have the given EJ, which means we completely skip that part. Related to calculations, final ones, meaning we don't count on units as such. So the fact that this little m will have a different dimension than the previous little m, which we calculated earlier, it is MB for the account. Let's call it MB phi. It doesn't matter much to us. Let's pay attention to the fact that here, it actually has a dimension of 1 per meter. If it has 1 per meter, then it is dimensionless. We simply have meters times 1 per meter, which is unity. And at this point, we have the following situation. Here we got 4/6. In the negative, meaning we agree, that over 8. It has to jump to this point. On the margin, 4/6 is nothing else than 2/3. A bit of life. It has to jump by 1, meaning if it was minus 2/3 here, we'll give 1. We'll get plus 1/3. It converges to 0, of course, because understandably in this situation, on both ends of the beam, we need to have 0, because it is unburdened. Here we have supports and the end of the beam. Supports and the end of the beam, moments at the ends of the beam. In this case will be 0. Now then, we only arrow this using this simplified formula from the tables. On our website, you have both versions. It looks like this. Now let's only do the simpler version. So we get this. Phi, which is the angle of rotation at point B, is equal to 1 per EJ. And we note the graphical integral. In the interval AB, we have it the same as before, 24 in positive. Here this will be relevant. The length of this interval is 4 meters. However, note here, this is in the negative. We have 2/3. In the middle, we write minus. Add. Here, 44. 40 and 10. Also on the plus side, it's 2 meters. And here we have 1/3, similarly to above on the plus side. So let's calculate it. Quickly, 1 over E. Let's recall what this formula looked like. L6, that is 4/6. 2 times what's after the same. 2 times 20 times 0. I skip. 2 times 40 times 2/3. But notice, 40 is significantly 2/3 negative. So we write minus 2 times. 40 times 2/3. Similar here. 40 times 0. 20 times 2/3, but that's minus plus. So the whole thing is minus 2/3 times 20. Analogically, 2/6. 2 times 40 times 1/3. Add 2 times 10, 0 we skip. 40 times 0 we skip. 10 times 1/3 we take. So quickly let's calculate it. We need 4/6 times. Minus 2 times 40 times 2/3. Minus 2/3 times 20. Add 2/6 times. 2 times 40 times 1/3. Add 10 times 1/3. We get minus 310 over 9. 1 over E. So minus 310 over 9E. And that really finishes the task. The result matches what I calculated earlier. So let's hope it's okay. I'll link you, either in the description of the video, or if I manage, then probably in the description of the video. Let's assume it's in the description of the video. In the description of the video, you will get a link to the formulas we used here, and will use in similar tasks of this type. Plus, you'll get a link to the solution of this task on our page. Additionally there, besides what is here, there will be a discussion related to units. Therefore, it's worth checking everything. For the most part, it doesn't help, but it might actually be required from you. And besides, it's worth knowing that it has some practical application and relation to reality. And Phi B will be done, using the definition, examining all these with a breakdown into components and so on. However, generally the principle of solving is the same as here. I encourage commenting. We read comments. We try to respond. If we don't respond, we definitely read comments, and we try to somehow refer to them later in what we record. Regarding this topic, that's all. Many thanks. Regards.